So please refresh the web page if you are not seeing that update. Refresh it. You'll see homework 1 is due Wednesday next week. So we're going to have a quiz on Wednesday, because I think if you turn in the homework, you'll be ready for the quiz. All right, and homework 2 will be something else, covers semiconductors, BJTs, which is something we didn't cover in analog. PNP, NPN, all these different kinds of transistors. And briefly, some examples about CMOS, MOSFETs, right? And then we'll dive into C5 layers in detail about every single layer in the chip. Okay? Right. First, let's finish the ADC, SAR's ADC, Wednesday. A little left over here. So remember that we need a sequencer at the bottom. Sequencer. They are nothing but just D flip-flops. And we have 5 at the bottom. Clock, 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 clock. If I just draw this symbol, but not a little bubble here, you know that this is rising edge trigger. D flip-flops. And set, reset. So for the very last one, just ground it, doesn't matter. And on the top, you need a code register. But let's finish this first. And every single Q should be shorted to the clock in the previous stage to trigger what? Trigger the D flip-flop. And comp, which is a comparator's output, is being shorted to all the Ds. Anything else here? That's it. Then, so everything here is a sequencer. All right. Because we need to set every single D flip-flop here sequentially. So we need something to do the job for us. You cannot manually do it by yourself, right? You need another circuit on the top. So it's called the code register or shift register on the top. Similar to whatever you are using here for the sequencer. S, 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 S. Reset, 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 reset. Clock. Do you need a Q here to trigger the clock here? No. You just need a universal clock. And you need a wire here. You can name it whatever you want, right? I just name it reset. But actually setting the first one. And the reset is being shorted. So this signal line is being shorted to the set of the first D flip-flop. and also being shorted to all the reset for all the following ones. Okay. And the Q, yeah, I'll just give you a really quick question here. So now, if reset is 1, what's going to happen? If reset is 1, at one moment, reset is being put up to VD. What's the output here? OB. If reset is 1, do I have an S bar here or S? S. It's not S bar. So whenever I have a 1 here, it's going to trigger the set function of the D flip-flop. So what's going to happen to Q? Q will be 1. So Q will be set. Okay, remember the table? We need an initial state which is 1, 0, 0, 0, right? As to start with. So this can do the job. I just give a 1 here, so it's going to set Q. So Q will be 1. However, I need a 1 to appear here because here is a data output. Let me know what are these what are these 4 bits? Which is MSB, which is LSB? Is this the output of the DAC? Of the SAR? Yeah, forgot the structure. What is this part? What is this part? So what is this? Entire thing here, what is this? Remember the SAR ADC? You need a being being shorted to a sample and hold circuit, and then a comparator, and then a SAR register circuit, and then 4 bits, and then the DAC, and here's the VREF, and this is being fed back to the comparator. So this is, so these are all the bits, B3, B2, B1, B0. So this circuit is this guy. So that's a symbol for everything here. All right, we're doing the most important part in the SAR ADC right now. We are trying to design it. So we already know what the DAC looks like R2R ladders, all these kind of things. There are other structures as well, but we know what is the DAC, and we know what's the op-amp. And sample and hold is just something similar to this, like this. All right, just so here's the sampling switch. Just turn it on, the charges flows into the cap and hold it. All right, so here's the sample and hold. That's pretty much everything for the ADC. But there will be some better design for the sample and hold circuit, and better design for the op-amp, and better design for the SAR, also the DAC. But let's just take a look at what are these very simple version of everything here. So SAR is whatever here, and you can see the SAR has 4 outputs, or 4 bits of output. If this is a 4-bit SAR ADC, so are these the 4 outputs of whatever here? These 4 lines, these guys, is that correct or not? And which is MSB, which is LSB? Think about it. Yeah, here's the LSB. Here's the MSB. Right? So 4 bits. And that's the output of the SAR circuit. And so we need a set every single D flip-flop in the sequencer sequentially. So the first one will be here, because this is MSB. And since we are, at the very beginning, we put a 1 at the reset signal line, and this becomes 1. So we just directly short this Q output to here. So after this one is set, it's going to set this one as well at the same time. Remember, the purpose of whatever here on the top is to give a 1 here and here and here in a specific order like this, right? Just one by one. We assume we can do that before we have this circuit, but now we need to implement it. We need to make it work in the real life. So we need something like this. How do you do that? The first, at the very beginning, you set, you give a 1 to this line. It's going to do the job to set this first D flip-flop. And after that, give reset a 0. Then what's going to happen? If you give a reset a 0, what's going to happen here? So at the very beginning, because the set and reset for all the D flip-flops are going to be activated by 1s, right? So if you have a 1 here, it's going to set this guy and reset all the other ones. But now if you give reset a 0, it's not going to do anything to the D flip-flops, right? You just release all the D flip-flops. And now the D flip-flops will be controlled by the clock and whatever the input is for the Ds. So now I'm not completing this circuit here. Can you just let me know what else are missing, still missing, and what are the connections I need to make? There are several connections I need to complete before I move forward, right? What are these connections are missing? Let's think about it. So the purpose of the top part is to give a 1 here, and then the next clock, shift the 1 to here, right? So I want to shift this one to here. How can I do that? And this one should be transferred to here. If I make this connection and just do this, all right, then what else is missing? Still missing. So think about it. At the very beginning, I put a 1 here, right? At the first clock cycle, I put a 1 here. All right, so it's really nice because all the other D flip-flops will be reset. So these Qs will be 1s or 0s. 1s or 0s at the first clock cycle. 0s, right? They are reset by this 1. See? Only this one is 1, but all the following ones are 0s. So which means all these ones are 0s, but only this one is 1. Okay, that matches the first state we have for the SAR. And next cycle, right after the first one, I give reset a 0. Then all the D flip-flops will be released, and they are going to be controlled by clock and D, whatever D is, right? So from the previous cycle, D here was 1 or 0. 1 here, 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 0s, right? So when the clock arrives, rising edge, what's going to happen? This one will be transferred to here. This 0 used to be 0 will be transferred to here. So what is the value here? Still 0. Here, still 0. Here, still 0. Only this one becomes 1. So what about this guy? Do you need it to be 1 or 0? Look at here. Do you need this guy to be 1 or 0 for the second clock, for the second cycle, according to the SAR? Do you still want to set it? Do you still want to set it at the second cycle? No, remember when you are shifting all the ones to the right, you only have 1, 1 here. So this 1 is being shifted to the right, and there's only 1, 1. Because after that, you are plugging in the comps in the front, right? So only 1, 1. So you don't want this one to be 1 anymore. Is that true? There's only 1, 1 being shifted to the next stage sequentially. So that one at the second cycle, it was transferred to here, which is nice. So this is being set to 1 as planned. And all the other ones are still zeros, which is nice. But what about the first one? You need it to be 0, right? And you need it to be 0 in the future. Why? Because you don't want to set this. You don't want to set this D flip-flop. And what you need at Q is actually comp, but not set. Because comp is being shorted to D. So whenever this D flip-flop is being released, this cycle, this Q signal is going to trigger the D flip-flop and transfer comp to Q, which is the final MSB. So anything else I'm missing here in the circuit? After the first cycle, I need this one to be 0. And in the following cycles, it needs to be 0. Always. Because I don't want to set this D flip-flop. I want to release this D flip-flop. So D can be transferred to Q, but not being forced to be 1. Same for the other ones. I don't want to set it because 1 will be shifted to here. And this will not be forced to 1 anymore. Because this is being released. This is 0. And only being triggered by the next Q. And for the rising at the rising edge. So what else I'm missing? And after that, I'm done with the SAR. So the only thing I'm missing is, because it's pretty much can do everything, but only one thing is, after this one was transferred to here, and all the following bits in the front should be zeros, but not ones. Only 1, 1 will be blocked or be saved in all these signal lines. So the 1 is boom, 1, 1, 1, 1, like that. So I can have 1, 1, 1, 1 here, because it's being shorted to here. Only 1, 1, not 2 or 3. But I need all the front bits to be zeros. What about that? After the first one, because when I have a 1 here for reset, this is not working. This is not being activated, so it's not being transferred to here. Because I'm forcing this one to be 1. I'm setting the D flip-flop, right? But after that, after I give reset a 0, the D flip-flop is activated. So this 0 will be transferred to here. And also in the future, it's going to keep feeding the zeros to the circuit. And that's everything for the SAR. Done. They are doing the homework. Probably there's one problem ask you to draw the structure of the SAR and explain the operation procedure. So this is what you want to do. Draw it and explain it. What's going to happen. What's happening here. See, there are some other homework assignments I want to explain a little bit. It's due Wednesday. Just want to say it again. The first one, determine the number of quantization levels needed if one wanted to make a digital thermometer that was capable of measuring temperatures to within 0.1 Celsius accuracy over a range from this to this. So what resolution the ADC needs, right? Think about it. So from minus 50 Celsius to 150 Celsius, and with a 0.1 Celsius accuracy, if I do this, 150 minus this, 200, right? 200, but you have one more. It doesn't matter if you don't have this one. It's not a big deal. So totally 201 steps actually. And divided by 0.1 Celsius, so you're getting 2010 steps. So how many bits do you need to achieve this many quantization levels? So it's going to be 2 to the n's equals to this. So n equals to, right, just do a calculation. That's 1.1. What about 1.2? Yeah, it's pretty simple, I think. Remember the full scale value. What is the full scale value? Which is 2 to the n's minus 1. Is that right? Over 2 to the n's, which is voltage full scale. And the third one, DACs, DNL, INLs, INLs. So INLs are asked in 1.4, but the same numbers here. So I recommend you do it in this way. Digital input. Let's just draw the chart first. Voltage. So if you draw the chart yourself like this, and what are the ideal outputs? Definitely these are not ideal ones because they have quantization errors. And I didn't tell you the voltage range over here in the problem, because if you look at this value here, the first step, and it's a 3-bit DAC, so kind of know that 2 to the third times 0.625 equals to V ref. So you have this is the first step over here, and you have a 3-bit DAC. So you know that this is V ref, which is 5 volts. So given that the V ref is 5 volts, and you know the every LSB is 0.625 volts, so the ideal output should be this. Wait, is that right? 1.25. Yep. And then 1.875. And then 2.5 for the next. And then 3.125 and 3.75, 4.375. Just add 0.65 to the next stage. And after that, you just draw the curve. To the curve, like what we have on the website. So I already attached the PDFs on the website, so you can look at all the examples here. This one, for DAC and ADCs. So if I have that, all the numbers here, and I can draw that transition curve. So there are 8 states. So DAC. That will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. 101, 110, 111. Wait, am I missing? Oh, let's draw one more. Okay, and it should be linear until here, right? Should be linear. And all the steps. So the voltages are all the ideal voltages, right? So they are here. But however, the values are not like whatever the ideal outputs are. So after the first one, so the real life transition curve looks like this. 0 is still 0, no problem. And 0.625 is still 0.625. So it does this, whatever the ideal curve gives you. But after that, it jumps to 1.25, not 1.5625. No, it jumps to 1.5625, but not 1.25, right? So this is the ideal output. This is a real life output. So 1.5625 is higher than this and lower than this. So it's in the middle. So what's happening here is this, right? Because this input is a DAC, it's converting digital to analog. So here's a 010, that's a digital input. It's giving you this analog output, which is higher than what it should be. It's higher than the ideal value here. And next, 011 is giving you 2, which is also higher than the ideal value. Here. And 2.5 is 2.5, which is the same level. So for the next transition, it goes to 2.5, no problem. And 3.125, also, no problem here. And 3.4375, which is lower than the ideal value, which is 3.75. So it's lower than that. Stop by here, right? And eventually it reaches final value, final voltage here. All right. How to calculate the DNLs? Based on this curve. The DNL is the real step width minus the 1 LSB will be the DNLs. So you are going to have a DNL here. So that will be DNL2. DNL0, DNL1, which is 0, DNL2, which is not 0, so we need to calculate it. And this step width is larger than 1 LSB. So what's that step width? So what is this step width here? See, here is 0.625, and here is 1.5625, right? So just use 1 point minus this and over 1 LSB. So you are getting how many LSBs for the error, right? So this minus this is this real step width minus whatever here, because it starts from here and shoot to here, so that's the width. And over this, and you are getting how many LSBs? And minus 1 LSB. And you are getting the DNL2. Is that clear? And the result here is actually 0.5 LSB. So next, do we have DNL3? DNL3 here? Is there a DNL here? So let's look at it. It should be this, but you are getting this. So which minus which? Which minus which? So you can get the step width here. Are you going to see the step width here or from here to here? Which one you want to look at? This or this? This or this? This or this? For DNL3. This, right? Because that's the real step width from here. Because that's the right lines are the real curves of the transitions. So the real transitions. So the previous voltage level was here and shoots to here, so that's a step width, which is DNL3. And you need to use the step width minus 1 LSB. Okay, so how do we get the step width here? Because you know the voltage here is 2. And you know the previous voltage level is 1.5625. So DNL3 equals to 2 minus 1.5625 over 1 LSB, which is how many LSBs for the step width here? How many LSBs? Minus 1 LSB will be the DNL3, will be the DNL error here. I got minus 0.3 LSB for this one. Is there a DNL here? DNL4. It's going to be this width, right? So that one is, look at 4, it's 2.5 minus 2. Equals to, let's see, minus 0.5 LSB. I'm going to, so there are other ones as well, like there's no DNL here because it's perfectly 1 OSB, but there will be a DNL here and also DNL here. This is wider than 1 OSB. This is smaller than 1 OSB. Okay, so you want to have these two DNLs here as well. So that's for DNL. What about INL? INL. Right. INL. Which is in compared to where? For all the INLs. Yep. So let's take a look at it. Do you have INL at 0, 1? So look at right lines. It's perfectly matched to the black ones. So no INL here. Here, which minus which? The real minus ideal, right? So what's the real value here? I will just give you one INLs and you are going to calculate the others. So what's the first INL you have here? 2. 0, 1, 2. And which minus which? See here, 2, that's the real value here, and that's the ideal value, right? It's this minus this. So it's actually here. That's INL2. So it's going to be 2 minus, is that 2? No, it's not 2. It's, no, sorry. It's this minus this, right? 1.5625 minus 1.25 over 0.265 minus 1 LSB. And this is 0.5 LSB. Do you have a INL here? Because the right line shoots to here, and the ideal line is here, right? So you want to find out the gap. What about next? Do you have an INL here? Nope. Nope. No INL here. Here? Nope. Here? Yes. And it's negative because the real one is lower than the ideal one. Here? Nope. Same value. All right. So I know how to do this. So what if I swap these two columns and make it ADC, not DAC? That's DAC. it's a little bit different. You need an ideal input. So which means that the ideal analog voltage input which can trigger that digital output, because you have a specific number of digital outputs, right? But in real life, it's not necessarily to be the ideal voltage levels to trigger that digital output. So let's use the same values here. So we can compare 0, 0.625, 1.625, 2.0, 2.5, 3.125. Ideally, not ideally. So the digital output, you only have 8 different combinations. So these are the real analog inputs which triggered this digital output at the DAC. But however, they are not ideal. So the ideal ones should be all these values has a 1 SB as a step size, right? So it should be this same value as here. So if you draw the curve for this ADC, it looks slightly differently. So what is x-axis here? Analog input, right? So there are supposed to be all these values. And I have 8. 1, 2, 3, 4, 5, 6, 7, 8. So 0, 0.625, 1.25, 1.875, 2.5, 3.125, 3.75, 4.375, and it should be linear. All the stars here for the ADC. Good. So these values are digital outputs. Zero 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 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. This should be the expected or the ideal voltages to trigger these digital outputs. But however, it's not ideal. So these voltages actually triggered all these digital outputs. And these are 1 point. So this is correct. So it's going to do this, no problem. What about the next one? 1.5625 is actually here. So it's going to do this. And shoot to where? It's going to shoot to which voltage? Output. From 1.5625, which is here. So it should trigger the change at this point, but it didn't. Right? So it's going to last until this voltage and then trigger the transition to where? You don't have many choices. It's an ADC. Yeah, it's an ADC, right? So you only have these outputs. You don't have other outputs. So shoots to where? 0, 1, 0. What's next? 2, which is in the middle. This is 1.8, this is 2.5, so 2 is in the middle. So it's gonna wait until 2 and then shoots to 0, 1, 1 because of this. And next, 2.5. And next, 3.125. Yeah, so this is accurate. And next, 3.4375, which is here. So it's gonna trigger the transition here to 110. And next, 4.375, which is here. All right, so what are the DNLs and NLs? What's the first DNL? Are you looking at the y-axis or x-axis for ADC's DNLs? X-axis, right? Because the y-axis is always 1SB. So you are looking at the step width here. Wait, let me see. I think it's 1 because this is DNL 0, and which doesn't have any errors, and this is DNL 1, which has something, right? So just find out this width and minus 0.625. So what is this width here? You're going to use this value minus this, right? So DNL 1 is 1.5625 minus 0.625 over 1 LSB. So you get how many LSBs is this guy? And minus 1 LSB, which is 0.5 LSB. That's DNL 1, which is here. And DNL 2 is here, right? Find out DNL 2. 0, 1, 2, 3, 4, which doesn't have any error here. 5, 6, 7, right? Just follow all the steps. So what about NLs? What's the first NL? INL is the point which triggers the transition. So you just look at the points, not the width. All right. So here's the point 0, point 1, point 2, and you start having NLs. So the first NL is actually NL2 here. And look at the transition. That's a real transition. That's the ideal transition point. Just use this minus this. So which is 1.5625 minus 1.25 over 0.625 minus 1 LSB. All right, just follow this rule to do all the following NLs. If you forget the definition or the concept of the DNL and NLs for ADC and DACs, just go back to, if you have a textbook, just read the textbook. If you do not have a textbook, I have scanned the chapters for these examples again on the website, and you can look at it here. So these two scanned version PDFs. So read it. Prepare for the quiz on Wednesday next week. So for 4-bit SAR ADC, VREF is this, VIN is this, show the states of the ADC's output in the state diagram. Remember the state diagram? You have a VIN, have all the states. Okay. And hand draw the register level schematic of 4-bit. This is what I just did in this class at the very beginning. And design the master slave D flip-flop with the set and reset, which I mentioned. I gave you an example on Wednesday, right? Just replace the 2-input NAND gate as the output with a 3-input NAND gate. And the last one is trivial. You have done that in the first week. Any questions? Any question on anything? Is that clear? Good news is this problem is a DAC, it's not ADC. All right. Okay, we'll see you next week.